Hello, I'm going to go ahead and work a problem where you have basically a battery in series with a single resistor that then is connected to two resistors in parallel. It's not like the problem that we worked in our lab meeting last time, only I'm going to do a little bit more stuff with it, and I've got definitely some different values that I'm going to be using. So I thought I'd show you how to do this without Kirchhoff's loop rules or junction rules. It's just purely using logic and understanding how voltage and current works. So first off, let me start with changing my video to my document cam. Now let me get it in focus a little bit. Okay, so what I have here is a 3.0 volt battery, has a current I leaving the positive side. Of course, it's the short end, so that's the negative side, this is the positive side. It's leaving the positive side, going into a 4 ohm resistor, and then that wire will break up at a junction and go into a 7 ohm resistor and a 5 ohm resistor that are in parallel within each other. And then they'll come back to form, those two wires will come back to form a junction, and that wire will then come back to the base side or the negative side of the battery terminal. So just like when we were dealing with potential energy, you can call the zero of voltage anywhere, just like we call the zero potential energy anywhere. Remember, voltage is just potential energy per unit charge. It literally has units of joules per coulomb. So I can pretend sort of that if I measure with a voltmeter the voltage right here, okay, that voltage would be 0 volts. What I mean by that is I'd take my voltmeter and the black terminal I'd touch to ground, and the red wire from the voltmeter or multimeter I would touch to this point right here, and it would read the exact same thing. So then if you follow the circuit, obviously there's a difference, potential difference between, in an ideal battery, between the low voltage and the high voltage is in this case 3.0 volts. So right here, if I again stuck the black terminal on ground and the red terminal at this point on this side of the battery, we should get 3.0 volts. Now, if we assume the wires have 0 resistance and compared to the resistors they normally do, now this case I actually chose really small resistors, so that might not be that fair of an example, but we're going to pretend like it is anyways. So if that's the case, then as you go all the way around here and get to this point right here, that's still going to be 3.0 volts because we're assuming the wires have 0 resistance. So there's no reason for the voltage to actually drop. Now, once the voltage actually, or the current actually hits the resistor, obviously that's going to make a drop in the resistance. And in fact, that, or drop in the voltage. And in fact, that voltage there will be the same as that voltage there, which we've labeled as A. So that's the point A. If I ask you for the voltage of A relative to ground, I would literally mean touch the black wire from the multimeter to the ground and touch the red wire there, and what voltage would I read? Okay. So now that we do that, we can see, oh, well, that's the voltage. Let's call it just V sub A. So I'll put a little bubble up here again. I'm calling this voltage V sub A. And then, of course, right here would also have a voltage of V sub A, and right here would also have a voltage of V sub A. And since we're assuming wires have 0 resistance, we'd still be dealing with essentially 0 resistance from here all the way to here, 0 resistance from here to here, and then 0 resistance all the way to here. So in fact, this point right here would be 0 volts, as would be this point right here. And of course, this point would be VA, as would this point right here. Okay, so in other words, the voltage VA is really the voltage across the individual resistors, the 7 ohm and the 5 ohm resistor. Okay, and just like I said before, VA is the same as this voltage right here too. So 3 volts minus the voltage across the 4 ohm resistor gives us the actual VA. So in this question, we're actually asking you what is the equivalent resistance of all 3 of these resistors. In other words, if I took this battery and connect it to a single resistor, what resistance would that resistor have to have if the battery didn't know any difference? In other words, the battery still sent a current I out this way. And I'm also asking you, what is the current I? And we'll be able to use that once we have it. Part B is what is the current through the 7 ohm resistor, and part C is what is the current through the 5 ohm resistor. And then finally, what is the voltage at A relative to ground? So that's literally meaning, hey, what is VA that I labeled all over the place here? So to do this, what I'm first going to do is compute the equivalent resistance. So this circuit is actually equivalent to another circuit with a 4 ohm resistor right here and a R parallel resistor right here, where R parallel is the equivalent resistance of these two in parallel. Well, we know that 1 over R parallel is equal to 1 over 7 plus 1 over 5, which I like to do arithmetic so I don't actually have to use my calculator. So I'm going to call this 5 over 35 plus 7 over 35. That clearly gives me 12 over 35. So that R equivalent, or R parallel that is, the equivalent of the two in parallel, is actually equal to 35 over 12. Now, if that was 36 over 12, it'd be a breeze. It'd be, in fact, just plain 3.0. But it's actually 36 over 12 minus 1/12, and I happen to know that 1/12 is 0.0833. So I know that, in fact, the R parallel would be basically the R parallel would be 2.92 ohms. Okay, it'd actually be 2.9166666 on for infinity. So that's R parallel, but that's not the same thing as R equivalent. Now I'm going to replace the same circuit with an equivalent resistance. This time it's going to have only one resistor, REQ, and that's the REQ we're asked for. As you can tell, REQ is just what you get when you put the 4 ohm and the R parallel in series, and series resistor add, just like regular numbers. So I'm going to add 4 to 2.92, and that gives me R equivalent is equal to 6.92 ohms. Again, if I need to do any subsequent calculations, I'll treat that as 6.91666 just to carry it. So that's one of the answers for part A. Now part B is, hey, or part A, the other part that we haven't done is, hey, what's this current going through that little piece of circuit right there? Well, using Ohm's law, we have 3.0 volts, that's V equals IR. 3.0 volts is equal to I times 6.92 ohms. So clearly I is just going to be 3 divided by 6.92, which is in fact 0.434, actually 0.4337 amps, which I'm going to call to the proper sig figs 0.434 amps. So this is part A right here and right here, the R equivalent and the current I. So part B, they want to know what is the current through the 7 ohm resistor. Well, if I jump ahead and figure out what voltage A is, that's actually probably the easiest route, because I know right here the voltage is 3 volts, right there the voltage is 3 volts, and right here it's 3 volts minus the voltage drop in this, and the voltage drop in this circuit, or in this resistor, is just I, the current going through it, which we just calculated is 0.4337 roughly, times resistance 4 ohms. So in fact, the voltage at A, which is how much voltage across the 7 ohm, is just 3 volts minus whatever voltage drop I get in there. So the voltage drop across the 4.0 ohm resistor is just 0.4337 amps. Notice I'm using an extra digit in the intermediate calculation, and I multiply that by 4.0 ohms. And when I do that, I end up finding out that the drop in voltage is 1.7350 volts, which means voltage A is actually equal to 3.0 volts minus 1.735 volts, which is equal to VA, which is 3 volts minus that, is about 1.265, or I'm going to call that 1.27 volts. So that's actually my answer to part D, which I took out of order. Now, this isn't the only way I could do it. There's a lot of ways I could do it, and I'll explain a couple more of those in a minute. But right now that I have VA, I can realize, oh, the voltage across the 7 ohm resistor is just VA. Same thing with the 5 ohm resistor, so I can easily calculate the currents through it. So for instance, Ohm's law tells us that VA is just equal to the current through the 7.0 ohm resistor times the resistance of the 7.0 ohm resistor, which means that and again, it was 265, so I'm going to write 1.265 volts is equal to I 7.0 ohms times times 7.0 ohms, and this gives you I through the 7.0 ohm resistor is 1.265 divided by 7, which turns out to be 0.1807, which I'm going to call 0.181. So the current through the 7.0 ohm resistor is 0.181 amps. Similarly, VA is equal to the current through the 5 ohm resistor, 5.0 ohm, times R of the 5.0 ohm resistor, which gives me 1.265 volts equals I 5.0 volts times 5.0 ohms. And again, I'm not really using strict sig figs because I only gave you 2 digits. In one case, I only gave you 1 digit on the resistor, but I'm sort of pretending like both resistors are known to 2 sig figs. That's why I gave you 3 digits. But ignore sig figs when you're doing in-class problems unless I specifically ask you about sig figs. So from this, I get I 5.0 ohms, that's supposed to be ohms, not a volt, is equal to 1.265 divided by 5, and that gives me 0.2530 amps, or I through the 5.0 ohm resistor is 0.253 amps, which, like I said, strictly speaking, the way I've got it written, this should really be like 0.25, and that should be like 0.18. Similarly with that 4 being only 4, that messed up a lot of stuff. But either way, that gives you how to solve the problem. It also taught you a little bit about how voltage changes throughout a circuit. If I wanted to solve this problem without first finding VA, what I could do is basically I could do a loop rule right here if I wanted to, and then another loop rule here, and then use Kirchhoff's loop rules and Kirchhoff's junction rule. That would actually work out. It's kind of not the neatest way, not the easiest way. In fact, I think the way that I did it is the easiest way. But I think with that one, you should be able to make some sense on how this is done. I hope this helps. Again, here's the original problem. And here's the answers, running by very, very slowly, hopefully. I'm doing everything in backwards, so it works really, really a lot harder than it is. All right, there you go.